Okay, and we're back. We're just going to do a quick intro to orders of magnitude, which are in your book if you ever need them. Then we're going to jump into power. The biggest mistake that people make who are new to the energy world is confusing energy and power. To the point that even experts confuse this and journalists confuse this, and it becomes an issue. But first, orders of magnitude. So let's start with your basic, we'll just use joules, which we can just write J. If you take a thousandth of a joule, what would you call it?
Microjoule.
Yeah, close. Millijoule, yeah. If we go down, millijoule. You've heard of millipedes? So, named because, not because they have 1,000 legs, but because they have, looks like they have 1,000. So we just call them a millipede. Centipede has a lot of legs, but not as many as a millipede.
But they're using measurement at that point.
What?
Measurement? Instead of...
If you take 1,000th of a millijoule, what would you have?
Is this the micro?
That's the micro one, yeah. Microjoule. Can't even remember the...
Mega.
No, that would be mega.
Mega.
So this would be, an order of magnitude, this would be 10 to the 0, or 1. Millijoule would be 10 to the negative third, or 1,000.
So you do 1,000.
10 to the negative third.
Why is it negative?
Oh,
That's
3
what I
zeros,
was, that's what one of
1,000.
my
Okay, I'll say.
questions. It's like, why is it negative?
Because
you're
it's
diminishing
moving
your
to
code.
the right.
You're going
back
Or
to-
bigger, yeah.
You're about like dividing. You're
Yeah,
dividing
the
3
decimal point
times.
to the right.
Saying 10 to the negative 3 is the same as saying 1 over 10 to the 3,
Okay.
mathematically.
Yeah.
So 10 to the 3 is 1,000.
Okay.
So 1 over 1,000 would be 1,000. So 10 to the negative.
Just consider it moving zeros and adding zeros.
So this would be, oh, what the, weird. Sorry, let's just skip that. This would be 10 to the negative 6. Well, let me erase it for some reason. So micros 10 to the negative 6. They're 1,000th thousandths. Don't ever say thousand.
What is the abbreviation for the microjoule?
For some reason, I can't remember it right now.
Okay.
Um,
It's easy enough to find out.
Wonder where the chart is.
yeah, can you find it? I always confuse it with the picojoule, which is a little,
I don't know.
oh no,
Weird
this is the
little U
microjoule.
thing, huh?
It's a mu. Greek letter mu.
Oh,
So it's like a U with a really long weird tail. If you go down another 1,000th, so 10 to the negative what? 9.
I'm just gonna guess.
It's used to describe certain kinds of very, very, very small technology. Nano.
Nano.
That's just an N. So now we're not lifting textbooks anymore. This is like a small bacterium lifting a small bacteria textbook in terms of how much energy it uses. Anyone know what's even smaller?
Pico?
Yeah, picojoule.
That's negative 12.
How are you gonna catch that? A little.
You probably won't be talking about picojoules too much in this class. But it's good to know what these terms mean.
I'll do the Pikachu joke. Did you
Oh.
catch the Pikachu joke?
Oh, that was awful.
Sorry.
You need to apologize to everyone online.
I really apologize. I think Pokemon, no.
Pokemon, oh, that was an even worse one.
It's
Oh,
even
wow.
worse.
Playing Pokemon No.
I didn't even know. That's even
Oh,
worse.
you already figured it out. I was yelling.
Oh, sorry. Missed the memo.
I was trying to find it as you were.
All right.
Did he catch
Well,
it?
what is that?
It's a weird little U.
Yeah, it's a
thing.
weird little U. What does
It's
that
a
even mean?
Mew. So Mew.
It's like that.
Oh, okay.
It looks like a U with like a teardrop coming down.
Mew. The sound a Greek cat makes. Okay, so that's getting small. And you'll hear these terms used again colloquially. So nanotechnology. It's not because it's technology that's 1,000th, 1,000,000,000th of the size of regular technology. It's just used to describe something that's very small. Same with micro. You've heard of microhydro? Yeah, it's not actually a millionth of the size. It's to describe something small. Let's go up. So instead of getting small, let's get bigger. So 10 to the positive 3, or 1,000 joules. Kilojoule. Let's go up one more. 10 to the 6th. Megajoule. Yeah, don't confuse your megas and your millis. Or your micros. Ten to the 9th. Giga. We have to move over here. Say
Is it Terra?
10 to the 12th? Yes. Yeah. Let's keep going. You guys are doing great. Excellent. Yeah. Exajoule. All right, that doesn't turn out. So these are just unit magnitudes you'll get used to as time goes on. But I want to show these because these are, when we talk about orders of magnitude, there's things that's on kind of the personal scale, the household scale, the city scale, the scale. So in terms of how much energy you use in a year in your household, that's closer to the megajoule scale. Megajoule to gigajoule. Energy in a year. In terms of the whole globe, it's in the exajoule scale. So we're talking billion textbooks being raised. Are there any questions about these?
So like your your reader on the side of the house, you know, for what your energy is usually kilo, like your the usage.
No.
Watts.
Watts?
Yeah.
Not even watts. Not even hertz. Well, they use hertz. That's something different. Hertz isn't energy. Watts isn't energy. Volts isn't energy.
Shush.
No one knows what's going on. We got units all over the place.
So it's like the cloud, like Apple Cloud, you know, like that's how that works either. Cloud,
Yeah.
where where all your information goes.
What does this have to do with exajoules?
I don't know.
Okay.
Just that.
No one knows what's going
Well,
on.
exactly.
No one knows what's going on.
That's really the
It all
connection
comes
there.
back to no one knows.
It's like no nuclear power. No one knows. Right? We're all just scared. Okay, so let's talk about that. You get the units of energy. You got joules, calories, BTUs. There are more that we'll talk about later. But we need to differentiate these with power. Power and energy are not the same. So give me a colloquial usage of power.
You have the
Force.
power.
You have the power.
I'm not forced to do something.
Force to do something, all right?
I'm not forced to like do something, I guess.
So if you want to move this table, the more force you have, the more power. Okay. Yeah, it's a good colloquial term.
Yeah, I feel like saving power. I think people like, you know, like,
Right.
I don't know why, but.
And they use save energy, save power kind of energy.
Yeah, I think that works.
What about,
Or like even like power, social power, like.
like who's powerful?
Yeah, exactly.
Donald
It's almost
Trump.
like so it's like authority. People use that word a lot.
Okay, yeah. You had your hand.
Well, it has something to do with what she was saying, but perhaps knowing all those different units we were spouting out, the actual definitions of those, knowing those would be helpful.
Okay, knowledge is
Oh,
power.
I see what you're saying.
Oh.
The knowledge is power.
You're tying it back into class.
There you go.
Nice.
Because then we would be able
Nice
to
keeping us from going
be
too
more
far.
efficient in our spouting
Aha,
engine.
I like this. I really like this. Okay, so let's say you had to do some Energy 101 homework. If you didn't know those units, it would probably take you a while to do the homework, right? You'd have to go look things up, you'd be confused, you'd throw your book at the wall, you gotta go buy a new book, you gotta sit down and
Pretty
do
much
it.
what it is.
Wow, it's a
Depends on
lot
which
of
wall
jewels
you
to
throw
destroy
it
that
at.
book.
It depends on the wall, you gotta the wall. So now knowing the units, you can do the homework faster. In theory, conceivably, you could do it faster. To the same level of quality. That's the difference between power and energy. Energy is the ability to do the homework. It's going to take a certain amount of energy to do this homework, whether you have to throw your book at the wall or you're just going to sit down and do it. But how quickly you do the homework, that's power.
That's trippy.
Should be. Think about it in a social context. Let's say you want to protect Missoula parks from pesticides. Sorry, I had to think
I
that one.
do.
You do. If you are a undergraduate at the University of Montana, it might take you several years to get that done. If you are the mayor of Missoula, you could do it with a signature. That's power. He can do it faster because he has more power.
You should do it then.
You
Save
should
me a
tell
lot of trouble.
So you both have the energy to do it.
Yeah, we both have the ability and or capacity.
You have the capacity, yeah, but he
Yeah.
can do it faster. So that's
I'll let it right now. You have the power.
that's what power is. So power we say is the rate. I want to make sure I don't butcher this. So you could say this a few different ways. The rate of energy consumption, the rate of energy use, the rate of energy conversion. I'll use conversion, is that okay? If I say conversion, you understand that means turning like chemical energy into physical energy, light into electricity. Okay. So rate of energy conversion or consumption, depending on how you want to think of it. Consumption implies that once you've converted it, you can't use it anymore. But conversion is a more physically accurate term. So let's go back to the textbook. You asked, could a 2-year-old lift that textbook? Would it take more energy? And we determined it wouldn't take more energy for a 2-year-old to do it.
Ah.
You have more power. You can lift that textbook onto the table in under a second. It would take a 2-year-old, quite a while to do it. So you use the same amount of energy, but you have more power. Does that make you feel good?
Oh, it makes you feel better. I'm gonna go throw in the 2-year-old's face.
The
Got more
2-year-old.
power than you.
Yeah. So that's all it means. So if we do, let's do some units on this. Rate. What is a rate?
How fast?
How fast?
A rate is like time and distance, right? Or not distance, but it's,
But if you're talking about speed, it is time.
yeah, time and speed or time and reaching a goal, or it's hard to explain. But rate is, yeah, it is. It's time and distance, basically. Well, if you can measure distance as like a continuous movement. Does that make sense?
Wow, you just got like
I know, it's really difficult to explain.
cosmological on it.
Oh,
It's like space-time, but I don't know.
I know, the space-time thing.
Yeah. Everyone online got that? Space-time?
Yeah.
Great, okay.
Okay.
So let's go with the distance, the speed analogy. So
Yeah.
if you're talking about speed, how are you relating the units of distance and time?
So it's the amount of time it takes to travel distance.
Okay.
So rate is time. No, it's not. The other way around, distance over time.
Think about what's the
Yeah.
unit on your car speedometer?
What's the unit?
Miles per hour.
Miles per hour. Miles.
So it's distance over time. Got it.
So speed would be distance over time. So what's the rate? We're talking about power. It's something over time, right? Because it's a rate.
Yeah. It'd be joules.
Energy.
Energy.
Or if we're going to go straight to the units.
Yeah.
So these, sorry, in physics terms and science
Yeah.
terms, these are quantities.
Yeah.
Energy is a quantity, time is a quantity.
Energy,
units.
Unit by unit next.
Joule per
Over.
second is the base unit.
Got it.
So we got there. We got power. And it is 10:50. You mind if I go just few more minutes? You have to.
No, I'm good.
You're good? Okay, great.
Change my classes.
Anyone know the unit? So we have joules per second. Those are units. But we like to simplify them to 1 unit use per hour. Someone shouted it out. It's the watt.
What?
Named for?
Hour?
James Watt.
Oh, okay. You pointed all this equipment, I was thinking,
Yeah.
an
Oh,
inventor.
sorry.
I totally got your vibe.
I need to stop doing big arms in this class. Look at this.
James, what? James.
So if we were to do like a quick example, you're going to lift that textbook onto the table. Takes you 1 second. How many watts is that?
1
1 watt. Takes a 2-year-old 5 seconds.
Then it's 5
5
watts.
watts. It's a joule per second. I get it.
5 watts?
It's 5 seconds.
It's a fifth of a watt. Yeah.
Oh.
Math. Numerators, denominators. All right. So your power, we'll call you A, because you're an A student. You're going to lift the book onto the table. That takes how much energy?
What?
The book's a kilogram, the table's a meter. Oh, energy.
1 joule.
Joule. So it's going to take you 1 joule to lift the book. You're going to do it in how much time?
A second.
1 second. So you've got how much power?
Got a watt.
You've got 1 watt. Okay. Now you're a 2-year-old. B.
Baby.
B for baby. Also going to lift the book onto the table. How much energy does it?
It still only takes 1 joule, yeah.
It takes 1 joule. How many seconds does it take the baby?
5.
5 seconds.
So it's 1/5 of a watt. Nice.
Yes.
Good.
Yeah, math. And that 5 looks like,
A J. Very much so.
we're going to make this so pretty. power? You do,
You.
not the baby.
You're so strong.
So much better.
Okay, so, yikes. We did not get to, can I do a quick analogy? I know you guys have to go.
Sure.
There's a whole bunch of people outside who want to get in here. We think about this in terms of speed. We have distance and speed. Let's say you're driving at 60 miles per hour. After 1 hour, how far have you gone?
60 miles.
60 miles.
After 2 hours, how far have you gone?
120.
How fast are you going?
You're going 60 miles an hour.
We're going. After 3 hours, how far have you gone?
If you're still going 60 miles an hour, then you have gone 180 miles.
And how fast are you going?
60 miles an hour.
Okay, so your speed doesn't change, right? You're just consuming a certain amount of speed. You're doing a certain amount of speed. That sounded like a joke. Don't do speed. People online? But you're accumulating distance.
Yeah.
So this can translate directly into energy and power. So let's say you are using 60 watts, which is the typical power of an incandescent lamp. After 1 hour, how much energy have you used?
That's
You don't know the unit yet, which makes this fun. There's a unit of energy called the watt hour.
Hot hour.
So how many watts are you using?
1
watt
watt
hour?
hour.
1 watt hour. No, not 1 watt hour. What are you doing?
You made you think we're doing 60 watt hours?
6.
Gee whiz.
60 watt hours.
Oh, 'cause it's
How many
how
watts
many
times how many
in
hours?
now, right?
Really straightforward. After 2 hours, how much power is the light bulb using? Still 60 watts. How much energy have you used? 120 watt hours. After 3 hours, how much power is the light bulb using? 60 watts. How much energy? 180. This is why on your appliances there is a power rating of watts. Because that's just how much power it uses all the time. It's like speed. You would never say watts per hour or watts per day. That's just what it uses all the time. Energy is what's on your meter and on your electricity bill, Northwestern Energy. It's charging you per watt hour or per kilowatt hour. Because the longer you leave those appliances on, the more energy you're using. Is that clear?
Yes.
This is the #1 mistake in the whole energy field. No one gets this. They're always confusing energy and power. You'll read journal articles like, this power plant will put out 8 gigawatts a year. Like, why does the year matter? It's just an 8 gigawatt plant. It puts out 8 all the time. Like, the year doesn't matter. This year, next year, year after that, it'll still be 8.
But the year speaks louder than the actual unit used.
The year doesn't matter. They just like it. So, keep that in mind. This is my last class with you. Brad will be back. Have a lovely time.
Feel better.
Thank you.
Peter, yeah, you had to
Thank
do
you.
all this deal.
Will do. Turn this off.